Now we talk about what you sort of talked about flipping. We're going to talk about flipping things. Lecture 1-3. Inverse functions. So nice. Okay, we're going to talk about function inversion. We're going to talk about the conditions for invertibility. We're going to talk about finding inverses. And we're going to talk about restricting the domain in cases where you can't get an inverse normally. Okay, so let's talk about some inverse problems. Just some examples to get you all excited. Okay, suppose you have a bacterial culture and you find its population or population density as a function of time, right? Let's see. Population density of bacteria over time. Okay, and in what's called the exponential, or somewhat stupidly, the log phase of growth, the density looks sort of like that with time. Okay, and suppose you ask, well, if I want this density, what time do I have to collect my culture at? Okay, which is a question that comes up. Okay, so rather than asking what is the density at a given time, you're asking at what time do I get the density I want? Okay, and that's the inverse problem. Okay. When is my culture ready? Another example. Position over time. Okay, normally you know the position over time, and suppose someone wants to say, okay, at what time will you have this position? Or, when will you get home, honey? Three, radioactive decay. Okay, normally you'd have, as a function of time, what fraction of the parent isotope remains. But if you make a measurement and see how much of the parent isotope remains, what you really care about is how old is this thing. That's the inverse problem. Okay? You check the composition of the sample, and you figure out how old it is. And to do this thing to death, the last one, spectrophotometry. What's the concentration? Too low? Okay, spectrophotometry you'll do in 130L, probably, those of you who are taking that. Where you want to find the concentration of a sample by measuring its optical density, or absorbance. Okay? So you're going to make a curve of concentration on the bottom and optical density this way, and you're going to then measure the optical density of something you don't know and try to figure out the concentration from that. Literally the inverse problem. Okay? Good. Good, so all motivated and excited, yeah? So basically what we're talking about is now we want to flip the input and the output. Given the output, what was the input? Okay, now remember what a function was. A function was a rule that maps each possible input to exactly one specific output. Okay? All right, let's look at a couple of functions. Let's look at x cubed. Okay, 0, minus 1, plus 1. Or let's make it more interesting. 0, minus 2, plus 2. Okay, when you cube 0, you get 0. When you cube minus 2, you get minus 8. When you cube plus 2, you get plus 8. And so on. Okay? That's not all the real numbers. Okay? Good? Okay. Can you answer the inverse problem? If someone says the cube is minus 8, can you tell me what made that?
Yeah.
Okay, right? You can map backwards. Yes? And so, okay, basically, because you have a function and because every output only has one source input, you can map backward. Okay? So an inverse mapping exists. Okay, and it's given by the cube root function. Okay, you take the cube root of this guy, you get this guy. You take the cube root of this guy, you get this guy, and so on for all the reals. Okay? Okay, how about x squared? Obviously the answer is no, or why would I be putting this up? Let's look at x squared. 0 minus 2 plus 2. Square 0 and you get 0. Square minus 2 and you get 4. Square plus 2 and you also get 4. Sad, right? What's the problem here? Yeah, sure, if you know that the square is 0, you can tell me that the input was 0. But for everything else, you can't, okay? So if I tell you the square, you can't unambiguously tell me where it came from. Good? Okay, because there are outputs mapped to from more than one input. Okay, without the stuttering, there are outputs that are mapped to from more than one input. Okay? No inverse. Or no inverse function. Okay? Still good? Yep.
Wait, have you found the question about time, right?
Say it one more time.
We still use the quadratic for inverse questions about time, right?
Questions about, you're going to say one more last time.
If the question is asking you about time, would that still be fine? Because the negative doesn't matter.
Oh, I see what you're saying. Yeah, if it's one of those ones where the other solution is, yeah. And that's a restriction of domain thing, and we'll talk about that. Yes, good question. Yeah, that's the end of lecture 1-3. We'll talk about that. But still, quadratic could have two positive solutions, right? And then you're still in trouble, right? Yeah. Okay, good. Excellent. Okay, so what we're doing is we're talking about, can we run our machine in reverse? Running our machine in reverse. Okay, so what did we have? We had an input x, we feed it into a function f, we get an output y equals f at x. And what we're talking about doing here is feeding y equals f at x into a machine run in reverse, f inverse, and can we recover the original x? Okay? Okay, this is the inverse function of f. And again, what are we doing? We're swapping the input and the output, okay, in our treatment, right? This used to be our output, but now we want to treat it as an input to this function, okay? Or in other words, we want to view x now as a function of y instead of the other way around. Okay. F and f inverse cancel one another. Okay? So, arrow diagram. You've got some x, which maps to some y through f. Y is equal to f at x. Okay, and if all the conditions are met and you've got an inverse, you can map back to x. through f inverse. Good? So that x is f inverse of y. Okay? Go the other way. So what does that tell us? So if I apply f to x, I get this thing. If I apply f inverse to f at x, I get x back. Okay? Similarly, if I apply f inverse to y, I get the input. If I apply f to f inverse y, I just get y back. They undo each other. Or look at the machines. I feed x into f. I get f at x. I feed that into the inverse. The whole point is that we should recover the input. X. X is equal to f inverse at f at x. Hey, look at composition. Okay? For all x in the domain. They undo each other. Good? Again, similarly, if you feed the output, we'll say y equals f at x. If you feed the output to f inverse, you get the corresponding input. X equals f inverse y. Again, for those who can't actually see that, x equals f inverse at y. Okay, and if you take the function at the input, you expect to get the output again. Y. So y is equal to f at f inverse at y. F at f inverse at y. For all y in the range. Okay? Whatever order you apply them in, they undo each other. Good? So for instance, if the function was the cube function, this guy would be the cube root function, right? You cube the thing, you undo it by taking the cube root. Or you take the cube root, you undo that by taking the cube. Good? Okay. If you have a question and I don't see you, please shout. Yes?
Sorry, for the second one, have your arrows that smaller one that you need.
This guy?
Yeah.
Better?
Thank you.
Thank you. Invertibility. Which may be misspelled or made up or both. What did we say? A function can be inverted if a function can be inverted if every output is mapped to by exactly one input. Okay? To every output, there's only one arrow coming in. Good? Or in other words, the function never takes the same value twice. Okay? All right. Ooh, a slide. So, functions that do that are called one-to-one. Okay? Functions where each output comes from exactly one input. Cool? And remember what our one-to-one functions look like, right? They look like this. Right, that's what a one-to-one function looks like, right? There's no arrow pairing here. Okay, and if there was arrow pairing here, you wouldn't even have a function. Okay? Does that make sense? Little shoelace picture? Good? Okay, one-to-one, and that makes sense, right? You're mapping one-to-one in both directions. Okay? A function f is called one-to-one if the functional values are not equal whenever the inputs are not equal. That's just all we've been talking about. Okay? Again, this is all posted, okay? Okay. A function is invertible if and only if it is one-to-one. Okay? Write that down. A function is invertible or has an inverse function if and only if if and only if it is 1 to 1. Okay? The kinds of things we're talking about as one-to-one functions in this course are what some people call one-to-one correspondences. If you want to be really cool about it, what people call bijections. You'll see that word a lot depending on what you do. Okay, a function is invertible, has an inverse function, if and only if it is one-to-one. Okay, so let f be a one-to-one function with domain D and range E. Then its inverse function, f inverse, has domain E and range D and is defined by f inverse at y is equal to x if and only if f at x equals y for each y in E. Okay, that's all we've been talking about. Okay? Any questions about this? I'm sure it's coming. Yes, it's coming. Okay, here we go. Like a minute. Okay, remember this was the domain, this was the range. Okay, but when you talk about the inverse function, what are we doing? We're going that way, right? So the domain is now E, and the range is D. Okay, for the inverse. Okay. Right, now thanks to this definition, what are we saying? We're saying that the inverse and the function have exactly the same information. Okay? They have exactly the same information, but they just run in different directions. Okay? One goes from here to here, one goes from here to here. Okay? Let's stop there. Thank you guys. Have a wonderful weekend. Okay, last class we talked about inverse functions. We talked about what an inverse function is, some situations where you don't have an inverse function. We talked about how an inverse function and a function undo each other. And we introduced one-to-one, right? So we said a function is invertible if and only if it's one-to-one. Okay, and what does that mean? Every input gets mapped to exactly one output. Every output gets mapped to exactly one input, one-to-one. Good? Okay. And an inverse is a sort of, this is the answer, what is the question, right? You get the output, you want to find the input uniquely. Okay, today we're going to start by, I think we went through all of that. Today we're going to talk about this. We're going to talk about how to find out from a graph if it's the graph of an invertible function. The horizontal line test. A function is one-to-one if and only if no horizontal line intersects its graph more than once. Okay, you remember the vertical line test is the test for functions, the horizontal line test is the test for invertible functions. So you'll remember at the beginning we talked about x cubed and x squared. Let's talk about them again. Okay, that's the graph of y equals, that's the graph of x cubed. Does this pass that test?
Yes.
Yes, good. Right, no matter what horizontal line I draw, it cuts it at most once. And in this case, exactly once. Good? Yes, passes. So it is one-to-one. This is the graph of a one-to-one function. So it's the graph of an invertible function. Okay? We also talked about the squaring function. Does this guy pass? No. You cut nothing here. Here you cut once, but everywhere else you cut more than once, so it fails. So not one-to-one, not invertible. Good? And that's exactly what we said at the start. Okay, with our arrow diagrams. Is that cool? Okay, why is this important? Well, if you draw a horizontal line, we're saying that that output can be mapped uniquely to one input. Okay? But the problem here is that if I drew a horizontal line and it cuts more than once, it's cutting twice. So that output can't be mapped to one input, right? It maps to both of those, and that's bad. Okay? Does that make sense? Okay. If a function's monotonic, is it one-to-one? Increasing or decreasing? So if it's increasing everywhere, is it 1 to 1? Yes, good. Okay, you can see that from like, a simple, proof by picture, right? If it's increasing everywhere, it's going to be 1 to 1, yeah? Nothing's going to cut this more than once. You can also look at the definition, okay? If the point on the right is always above the point on the left, or if the point on the right is always below the point on the left, then no two inputs can give the same output, okay? So if it's monotonic everywhere, yes, it's going to be 1 to 1. Yes, it's going to be invertible. If it's periodic, is it going to be 1 to 1?
No.
Right, periodic's bad, right? You're repeating. So it's very not 1 to 1. Okay? Okay, if you want an example of something that oscillates. Okay. Right there you go. So you draw any horizontal line through this thing, not any horizontal line. You draw horizontal lines through this guy, it'll cut quite a lot more than once. Okay, so not 1 to 1. And that's just an example of a periodic function. All good? Again, these are the same results we had before. Okay. Let's talk about machines. Again, a way of thinking of a function, okay? That's going to be a composite function. Okay, so let's talk about this function. The cube root of 2x minus 3. Okay? Okay, if I want to look at that as a sequence of steps in machines, I feed the input in, and I double it. So 2 times the input. Then I subtract 3 from that. And then I take the cube root of that. Does that make sense? That's 2x. That's 2x minus 3. That's cube root 2x minus 3. Okay? And say you want to invert this thing. This whole thing is f. Okay, if you want to invert this thing, run the thing in reverse, go this way, and invert each of them. Okay? So apply the machines in reverse and invert each. Okay, so this guy first. Its inverse is the cube function. Then this guy. Its inverse is adding 3. Okay, the opposite of taking the cube root is cubing. The opposite of subtracting 3 is adding 3. They undo each other. The inverse of multiplying by 2 is dividing by 2. Okay, there we just get 2x minus 3. There we undo the subtraction and get 2x. There we undo the multiplication and we're left with x as desired. Okay? Apply the machines in reverse and invert each one. And that guy is f inverse. Okay? So f inverse of y is equal to, right up here, f inverse of y is equal to y cubed plus 3 all divided by 2. Does that make sense? Quick note and warning here. This, where shall I write this? F inverse y does not mean the reciprocal. Okay? This is not this. This is not this. Good? It's the inverse function, not the reciprocal. All right, we can find the inverse algebraically. Same example. Let y be the output. And solve for x in terms of y. Okay. Cube both sides. Add 3 to both sides. Divide both sides by 2. And that's your inverse. Good? Make sense? We did essentially what we did there, just with algebra. Yep? Yep.
Is the entire idea of the machine, multi-machine,
Can you say it one more time?
the idea of the entire machine,
Yep.
like visualization or whatever, is it to basically find the equation in the end?
For here?
So like the entire model that's
Yeah.
on the board,
Yep.
is the idea to get some...
Yeah, the point of this is to get this, yeah.
Okay.
And to visualize how it comes about, yeah?
And just, sorry, can you go back to the, this does not mean...
Yeah.
Can you just repeat what
Yes,
does
okay.
mean what?
This is the notation for the inverse function of f.
Okay.
It is not the notation for the reciprocal of f.
Okay.
Okay? Yeah.
Could we do one that isn't one-to-one, just to see what it looks like when it doesn't work out?
When it doesn't work out, okay, well suppose this was, what do we got? Okay, so suppose you had a square on the end here, right? So instead of cube root, you had squared, right? Now, suppose you try to undo that. What happens? You have a problem. You're going to get plus minus square root something, right? Right, if you try to solve. So you don't get a unique output. So you don't get a function here, and so the whole thing flops. Is that, okay. Good so far? Okay. Okay, in math, and I think they tell you this in high school, right, is to now interchange x and y, right? So you'd end up writing this thing as f inverse x equal 1/2 x cubed plus 3, something like that. And that's fine too. It's the same function, right? You can put a w there, you can put a dot there, you can put a z there, it doesn't matter. It's the dummy variable, yeah? Okay, but if you want to think of x as input, then yeah, you change x and y and you talk about x as input. Does that make sense? So you can do this if you want to. And last class when I talked about the inverse of the cubing function, I think I wrote f inverse x instead of f inverse y for that reason. Okay? Questions? Okay, again, in science and in the real world, variables mean something. Okay, so they're not just symbols that you put in willy-nilly like that and expect things to make sense. For instance, the radius and volume of a sphere okay, the volume of a sphere of radius r is given by this. 4/3 pi r cubed. Okay, if we invert this thing, how do we do that? Again, we solve for r. Okay? Multiply both sides by 3/4. Here, I'll do the whole thing. Okay, also divide by pi. And take the cube root of both sides. Okay? Okay. So you'd say that the inverse function is given by this. The cube root of 3 over 4 pi all times b. Okay? What you would not do is swap the variable names here. These mean something, right? You would not write, do not write v equals f inverse r equals 3 over 4 pi r cube root. Don't do that. That's something else. You've changed everything, right? The relationships change. That's nonsense, okay? In math, you can do stuff like that. They're just symbols. In the real world, they mean something, okay? Okay. Okay, we talked about seeing if something is invertible. We talked about finding it algebraically, the inverse. Let's see if we can graph it. Okay, that's the line y equals x. And here's our function. Okay, suppose you have a graph of a function f, okay, and you want to graph its inverse, presuming it has an inverse. So let's look at this thing. Let's look at a point on here. Okay? Let's say that's the point AB. Okay? I'm going to erase this too. So AB is on the graph of F. You don't have to write this bit down as long as you understand it. What does that mean? That means that F at A equals B. What does that mean for the inverse? That F inverse of B equals A. Good? So that means that BA is on the graph of F inverse. Good? B A is on the graph of F inverse. Is that good so far? Okay. And if you do that for all the points, you'll get something like that. F inverse. Okay? Now, if your geometry is good, you can figure this out geometrically, or if you're like me, you wind up having to use coordinates and algebra to figure this out, but you can convince yourself that the line y equals x is the perpendicular bisector of that segment. Okay? So that cuts at a right angle, and those two are equal. In other words, that point is the reflection of that point across that line. Okay? And so the graph of F inverse is just the reflection of the graph of F across the line y equals x. Good? You get the same result. Again, remember what you're doing. You're trying to interchange x and y, essentially. So if you went like this behind the board, you'd see the same thing. Okay? So if you looked at the graph of F like that, looking at this as if it were y, looking at this as if it were x, it's the same as doing that. Okay? But yeah, the way to graph an inverse function is to flip across that line. Okay? And that's what that says. We're good? Do I want to go here? No. Yeah. Okay, most functions are not invertible, right? If you make a function at random, it's not going to be invertible. Question is that even true? Okay, put it this way. If you have a function that's not invertible, you might be able to make it invertible by restricting its domain. Okay? For instance, how about this? If a function is not invertible, it may be invertible on a restricted domain. For example, we saw the squaring function is not invertible. Yeah? Not invertible. But this function is. Okay, if I restrict the domain to only non-negative x, it's invertible. Okay, you can convince yourself with an arrow diagram, you can convince yourself with graphs. So this guy looks like this, whereas this guy looks like this. That one fails the horizontal line test, that one passes it. Good? So if you restrict the domain, you can now uniquely map outputs to input. Examples. I talked about bacterial growth at the beginning. Okay, I talked about the exponential phase, and you want to know at what time you reach a certain population density. Bacterial growth doesn't just look like the exponential phase, right? You have a lag phase, then you have the exponential phase, then you have a stationary phase, then you have a death phase. Okay? So the whole curve looks a bit like this. That's not one-to-one, okay? But the bit that's exponential, for instance, is one-to-one. Yes?
Do you expect like word problems of that nature on the midterms?
This sort of bacterial thing?
Things where we're not going to have to restrict the domain in order to actually get a reason like a hexagon or something.
Well, you mean a word thing?
Yeah.
I'll let you know closer. How's that? Okay. Domain restriction is part of it. Whether it's going to be a word problem or not, we don't know yet.
I just remember them being
Fairly common? Is that what you said? I'll get back to you if it's something shareable. Yeah.
When would you restrict the domain to the negative side?
What's that?
When would you restrict the domain?
When would you?
Yeah.
Simply when that's what you care about. If I can cook up an example, I'll tell you. Yeah. Yeah, I'll tell you if I think of something. We're going to talk about something, well, either today or next time, where you get a negative answer, and it doesn't need a domain restriction, but if it did, then that would make sense. But we'll talk about it next time. Basically, when you're casting back to the past, it would make sense, right? So if you got a projectile and it's already in the air, and you want to see when it, when did Kim Jong-un? Yeah. Okay. Okay, similarly, if you've got a projectile like we just talked about, projectiles do that, right? So in general, they're not going to be one-to-one, and you'd want to restrict those. Cyclical things, like these guys. Okay, simple harmonic oscillator. So if you have a mass on a spring, and the whole thing isn't damped, and you let it bounce around, the position against time is going to look like that. Okay, that's just a sinusoid. And that's very, very not one-to-one. So if you just say, at what time is the position this, you can't really answer that. But if you talk about restricted bits of this, then you can. Okay? And similarly, because we've got biologists in the room, in the Arctic, the populations of lynx and snowshoe hares oscillate. And you're going to see this in 150 if you're taking 150. They oscillate together, there's a lag between them. But in any case, same problem, right? This thing isn't one-to-one. If you ask at what time is the population of lynx such and such, you can't answer that immediately. Okay, but if you ask between this year and this year, when is the population such and such, then you can. Okay? So you got to restrict it so that you've got something one-to-one, and then you can invert that. Does that make sense? Okay, one example here. This is the tangent function. Suppose you wanted to restrict the domain of this guy so that you still covered the whole range, but the function was one-to-one on the restricted domain. Do you see what I'm saying? So you want your restricted version to still cover everything vertically, okay, but make it one-to-one. Have you got a domain that'll do that?
Yeah.
You want to tell me?
X must be greater than negative pi over 2,
Yep.
but less than pi over 2.
That's perfect. Okay, good. Excellent. So if you restricted just this strip, yeah, you still get the whole range, but it's one-to-one, right? So in that restricted domain, yeah, you pass the horizontal line. Good? So for the tan function, we restrict it to, and we will talk about this later. That's one option. Okay? There are other options. You could go starting at 0, excluding pi over 2, up to pi but excluding pi. That also works. Okay, it's awkward, but it works. Okay? Questions? Yes.
If the range was 0 to pi, wouldn't,
Say that again.
if the range was 0 to pi.
Domain or range?
Oh, I mean the domain.
Yep.
Then wouldn't it not cross the horizontal line test? Because it crosses like at 0.
0 to pi?
Yeah.
0 to pi, yeah? And you're saying you complain here, yeah?
Yeah.
And I complain exactly the same place. That's why I said up to but excluding pi.
So would it be like one side of it not including 0 and then
Yeah, so
one
I'd
side
say,
of it?
yeah, so I'd say this. I'd say, or for instance, 0 to pi over 2, include 0, leave out pi over 2 because it blows up, and leave out pi because if you included pi, it and 0 would have the same output. Yeah? Does that make sense? Yeah, good question. Okay? And just one more thing, just to say this again, because this came up last time. X squared and square root x on their own are not inverses of one another, because x squared doesn't even have an inverse, okay? Okay, so you can't just go square root of x squared is equal to x. That doesn't work. It works if you restrict the domain, but in general it doesn't work. And we'll talk about that in the tutorial as well. Yeah?
Could you also restrict it to 0 to pi over 2 if that's all you need?
Yeah, sure. Is 0 to pi over 2? Excluding pi over 2? Yeah, that's something, but it doesn't cover the whole range, right? It doesn't cover all the features. Is that fair? Yeah, so later on when we talk about inverting or inverse trigonometric functions, we'll talk about that. Okay? Okay.